Welcome to redox reactions and intro to electrochemistry. By Jack Ezzell. So first, there's some vocab you need to learn. Electrochemistry is study of interchange of chemical and electrical energy. Voltaic and galvanic cells are battery, but not a dry cell. Generates useful electrical energy. Electrolytic cells require useful electrical energy to drive a thermodynamically unfavorable reaction. Oxidation is loss of electrons, so reduction is the gain of electrons, and you can use oxidation or you can use oil rig to remember that. Oxidation number is the assigned charge of an atom. So first we're going to learn oxidation state and how to determine it. So first you just got to look at the charge of the elements it's attached to. So in this example, manganese O4 minus, MnO4 minus. And you want to find the oxidation state of manganese, then you calculate in your head 4 oxygens with a charge of -2 times 4 equals -8. The overall charge of the compound is a -1, as you can see here. So the oxidation state goes to 7+ for Mn. Most pure elements and diatomics have an oxidation state of 0, and that's just one of many rules. So mini lesson on redox. So you split the reaction in two. You balance O's and H's with oxygen or with water molecules. Balance water molecules with hydrogen atoms, H+ ions. And then you usually have the electrons and the hydrogen or H+ ions on the same side. Then you have to make the electrons equal, so you multiply by an integer to get them the same, and then cross them out. And then you add the half reactions together, canceling out common terms. So here's an example. First you balance the elements that you can balance: 2 aluminum, 2 aluminum, 2 iron, 2 iron. Then you break it into half reactions, and then you have an oxygen here, so you have 3 waters over here, 6 H+ to balance out the H's in the water. Same thing down here, 3 waters, 6 H+, and then those cancel, and you get this reaction right here. Another example, this is an acidic solution. So here's where you have to multiply by a common multiplier, or not a common multiplier, just an integer. 7 electrons, it cancels out to equal this. And we know how to do redox. We've done it enough. Crazy animations. So here's an FRQ. Part A, identify the electrode at which oxidation is occurring. Explain your reasoning based on the student's observations. So oxidation is going to occur where there is a loss. And there's a chart that shows you the cell potentials and what it should be, but I don't have that in this picture because I just screenshotted the FRQ. Anyway, you can see that the SN atoms are going to be forming SN2+ and creating a drop in mass right here, which is the part B. So why does the mass of SN electrode decrease? It goes into solution, SN2+ ions. The salt bridge down here, KNO3. Where's the K going to go? K+ is going to go to the copper electrode, because that is the reduction, and the NO3 is going to go towards the tin because that is the oxidation, and that is the purpose of the salt bridge, is to restore those ions. So next part is it's going to go from a 0.1 molar to a 0.5 molar, but both of them are changing. So does the cell potential change at all? Well, of course not, because you're decreasing by the same concentrations on both sides, both cathodes. So both yeah, both whatever. But the standard and non-standard cells can be used to power electronic device. Which one would power longer, the 1 molar or the 0.5 molar? Or is there a decrease at all? Yes, there is. The non-standard cell would power the device for a shorter time because the supply of copper 2+ ions will be exhausted more quickly. Okay, one more part and then we're done. In the experiment, using the information from the table above, the net ionic equation for the reaction between the SN electrode and the copper nitrate solution would be thermodynamically favorable. Justify that the reaction is thermodynamically favorable. Okay, well the copper 2+, this is a redox reaction in itself. Easy to balance because it is, they both, copper 2+ goes to copper, SN goes to SN2+. And the cell observations from earlier parts of the question are evidence that the SN is oxidized and copper is reduced, therefore E must be positive. And that's really all. The rest is just thermochem, so it's not relevant. And that's it. Hope you guys enjoyed.